Hi everyone. In this short lesson we're going to cover the nomenclature that we use to distinguish alkene isomers from one another. Well, let's take a look at these two alkenes I'm showing on the screen here, and you'll see that we have sort of two different isomers. The isomer on the left has the double bond there in the middle, and we have the two methyl groups sort of on the same side in this picture on the bottom of the double bond. And then the molecule on the right, we have the double bond there again on the horizontal, and we have the two methyl groups on either side of the double bond sticking out on opposite sides of the double bond. Now, if you've taken AP chemistry or you know a little bit about alkene nomenclature, what you might be used to is referring to the molecule on the left as being the cis isomer, and the molecule on the right as being the trans isomer. And cis and trans for simple alkenes usually works pretty well, but as we get into more complicated alkenes, and we'll see some examples a little bit later, this cis-trans nomenclature can run into some problems, so we're going to need to actually adjust it a little bit and make it a little bit more unambiguous. So what we're going to do is we're going to take a look at a nomenclature that uses something called the Kahn-Ingold-Prelog rules. These are three guys who in the early part of the 20th century were working on nomenclature for isomers. They eventually met up all together and they kind of came up with some rules on how to assign configurations for isomers. So what we're going to do in the case of alkenes is we're going to take a look at each side of the double bond kind of on its own. So what I mean by that is we're going to look at the left side of this double bond, and then we're going to look at the right side of the double bond, and we're going to compare the two halves of the double bonds on their own. So let's go to the blue half of the alkene that's on the left. So in the blue half of the molecule, you see that we have a hydrogen, and down here on the bottom we have a carbon. So what we're going to do is we're going to compare that hydrogen versus that carbon to assign priority, and we're going to use atomic number. Carbon has the higher atomic number over hydrogen, so carbon here has a higher priority than hydrogen, and I'm going to indicate that by using a 1 and a 2. Now on the right side of the double bond, we again have a carbon and a hydrogen, and again carbon has a higher priority based on atomic number than hydrogen. So what we see here on the molecule on the left is that I have the two higher priority groups on the same side of the double bond. Kind of think of the double bond as being a fence, and we have the two higher priority groups on both sides of the double bond fence. So we appeal to some German here to identify the nomenclature, and so the higher priority groups are together on the same side of the double bond. And so we're going to use the German word for together, which, as you all know, is zusammen, and probably you don't know that, and we're going to identify this molecule as being the Z isomer of, in this case, 2-butene. And then the molecule on the right, if we go through the same analysis, all right, I have my double bond fence here, okay, and if I look at the part on the left, I have a carbon here, a hydrogen there, so again, 1 and 2, and then the carbon on the right, I have a carbon there, 1 and 2, and you see that the higher priority groups now are on opposite sides of the double bond fence. So we're going to refer to this as the German word for opposite, which is entgegen. So this is actually the E isomer. So in a way, Z molecules are sort of like cis molecules, and E molecules are sort of like trans molecules. But we're not going to use cis and trans anymore. We're going to use this Z and E nomenclature because it is a little bit more unambiguous. All right, let's take a look at another example. Is something we don't need to apply E and Z to. Let's take a look at this molecule here, and if we go ahead and we build our double bond fence, and we look at the carbon on the left, we'll see that we have off of that doubly bonded carbon two carbon groups. So there's no distinction between the molecule, between the two branches of the molecule on the left. Similarly, we have no distinguishing features for the double bond carbon on the right. So both sides of this alkene are symmetric. And so if we have symmetry about even just one side of the double bond, we can't have priority, right? I've got the same priority here as I have here, as I have there, versus there. So since I don't have any priority on either side of the double bond, then I can't really give this an E or a Z designation. So this molecule, if I were to go ahead and name it, this molecule would just end up being named 2-methyl-1-propene. All right, so there's no E or Z designation here. All right, let's take a look at a molecule that we could name with E and Z that gets even a little bit more. All right, we have this molecule here. We're actually not going to try to name this molecule, but we are going to just identify the E or Z nature of the molecule. And this one is a good one to look at because it gets a little bit more complicated. So first I'm just going to blow this up a little bit more, make it a little bit bigger. And if we start with the double bond fence, so here's our double bond fence, and I'm going to start with the carbon on the right. So here's my doubly bonded carbon and its branches on the right. You see here I have a carbon versus a hydrogen, so clearly that carbon with the higher atomic number beats that hydrogen with a lower atomic number. But now let's look at the branching going on off the left-hand carbon. You can see over here that things are a little bit more complicated. So if I start with my doubly bonded carbon and I take a step out, I have a carbon here and a carbon there. So I don't yet have any distinguishing features. Furthermore, I have one hydrogen on the bottom branch. I have a hydrogen on the top branch. I have another hydrogen on the bottom branch. I have a hydrogen on the top branch. And then I have a chlorine on the bottom branch and a fluorine on the top branch. So I actually have to work my way out atom by atom by atom before I can find a distinguishing feature. So it's the higher atomic number of chlorine that beats out the lower atomic number of fluorine. And so in this molecule, I have my higher priority groups, both of my ones, my one here and my one there, on the same side of the double bond fence. So this is going to be the Z isomer. So this example points out that sometimes you have to go a little bit further out on the branch before you find a distinguishing feature that allows you to identify E versus Z about the double bond. Let's take a look at an example as multiple double bonds. Now, if we have multiple double bonds, then I have multiple possibilities for my E and Z. So I need to treat each of these double bonds as their own E and Z. So what I'm going to do with this guy is I'm just going to rotate it a little bit so that we can see its double bond features a little bit more like the way that we're used to. So I'm going to start with the double bond here on the bottom left first. And before I do that, let's just remind ourselves that here there's a hydrogen, and here there's a hydrogen there, and there's a hydrogen there. So now as I go ahead and build priorities, let's start with the left-hand side of that carbon that's doubly bonded. So I have a carbon here and a hydrogen there, so that has higher priority. Then on the carbon on the right here, I'm comparing this hydrogen versus this carbon. So that carbon clearly wins over that hydrogen. So this first double bond has the higher priority groups on opposite sides of the double bond fence. So the left-hand carbon here, the left-hand double bond, is going to have an E designation. Meanwhile, if I go ahead and I take a look at the other double bond, and let me switch to some other color so we can see this a little bit more clearly, I have the double bond here on the left-hand side, or excuse me, on the right-hand side. So I'm going to compare this hydrogen and that carbon. So that carbon wins, that hydrogen loses. And then now the carbon on the left, which is still the carbon in red, this carbon has a hydrogen versus a carbon here. So in this case, for the double bond on the right-hand side, its higher priority group, and I'll do this, let's do it in yellow. For this carbon here, the higher priority group is that one versus that two. So I have, again, my ones on opposite sides of the second double bond. So that two is an E double bond. So when I go ahead and name this molecule, and maybe what I'll do is I'll just clean this up a little bit so we can see it a little easier. this molecule here now is going to have two E's. So when I go ahead and I name this molecule, what I'm going to have is, the way we indicate this is 2E, 4E, because that's where the two double bonds are, and I put those in parentheses, hyphen 2, 4, hyphen hexadiene. All right, because this is a hexane molecule with two double bonds, so it's hexadiene. So I have 2E, 4E, hyphen 2,4 hexadiene. So I've told you, again, where both double bonds are, but using the numbers, I'm also indicating the configuration about those two double bonds. All right, so let me add more molecule here that would be a little bit more complicated, and this one I think you can go ahead and name on your own. But now we have three double bonds, so that's three possibilities where you might have to worry about E and Z. But I'm going to give you a hint. You don't have to give an E or Z designation to all three of these double bonds. One of the double bonds cannot be assigned an E or a Z because at least one half of its double bond is not asymmetric. Okay? And, well, let me just give it away. This double bond here cannot be E or Z'd. Just make sure you understand why. And then when we go ahead and name this molecule, I'll give you another hint. Carbon number 1 is located right there. That's carbon number 1. So with those two hints, go ahead and see if you can name this triene molecule that also has an alcohol and an amine functional group, keeping track of the relative importance of alcohols over amines, numbering it correctly, and then giving its full name. All right, so we'll leave that for you to do on your own, and if you want to check your answers with me later on, you can do that. So that is configurations of alkenes. So with this video and the handouts we've given out in class, hopefully assigning E or Z to alkenes will be a little bit more straightforward.